Hi everyone and welcome to our presentation. Today, Sarah, Tissa, and I will be presenting on correlational research designs. Please refrain from asking any and all questions until the end of the presentation, and please hold your applause. Also, please excuse our use of technology. Despite all of our rehearsals, we may still struggle just a little bit. So to begin today, we're going to talk about correlational research and why we use it. A correlation is a statistical measure that indicates how sets of data fluctuate together. This data can be positive or negative, and Tissa is going to get into a little bit more of how that looks later. We use correlational design when we want to understand the relationship between two variables. So for example, does a sense of humor impact success in the funeral industry? Or does success in school be impacted by attendance or participation? We may also use correlational design to understand and predict future outcomes. Not exactly like weather, but for example, does a student's secondary school average predict their success in post-secondary studies? Or for example, what factors are the best predictors for impacting the spread of COVID-19? Also a correlational study. Correlational design is quantitative, meaning that data is from random sampling from a large group of participants who have a minimum of 2 sets of data taken from them. Now for a history lesson. Correlational research was developed by a gentleman named Carl Pearson in the late 19th century in England following the creation of Galton's theories and Darwinism. They presented concepts such as importance of sample size, the value of precise measurements, and the use of unbiased samples. In 1897, Ewell, one of Pearson's students, developed solutions for correlating 2, 3, and 4 variables, as well as advanced the theory of regression and the ability to predict scores. In 1904, Spearman published ideas about the correlation matrix to display coefficients and an advanced formula for the data that didn't fit the regular bell-shaped curve distribution we're all used to seeing. Furthermore, in 1935, Fisher pioneered significance testing and analysis of variance, which is important for studying the difference between observed and predicted scores. In 1963, Campbell and Stanley thought that other experimental designs were more vigorous and valid than correlational designs because they were the mean girls, and they outlined the threats that they could see to validity in using this type of research. Fast forward to the 70s and 80s, computers became a more useful tool in data analysis, particularly when it came to correlational design. It allowed for isolation of variables and formulas for easier and more efficient study. This translates to today, where researchers can test a plethora of elaborate models for many different variables due to our technological advances. So when there are only 2 variables, they share common variance or they covariate together. This means that we have the ability to predict one score if we have the other. Please note our lovely graphic. Correlation implies causation. False. It measures the degree of relationship between variables. So for the product moment correlation coefficient, it's also called zero order correlation, the Pearson R, or the bivariate correlation. As shown in the photo, the statistic is calculated for 2 variables by multiplying the Z scores on the X and Y axis and then dividing the number of cases minus 1. It measures the strength of association between 2 variables. And we're going to talk a little bit more about this further in the presentation. So what we want to know is when to use correlational designs. So there's 2 major categories, one being explanatory, when a researcher wants to find the extent of which variable affects another, and prediction, when a researcher wants to make a forecast or a prediction about an outcome. I predict we're going to get an A on this presentation. There's no research to back that up, though. So if you want to use the explanatory design, you're going to want to look for correlation of 2 or more variables, researchers having collected data at more than one or at only one point in time from one particular group, They also, in that study, there would also be the use of a correlation statistical test in their data analysis. And then the researcher will also make interpretations or draw conclusions from those statistical test results. So I took an example from the textbook for explanatory design. So bear with me. So this was from Anderson and Keith in 1997. They wanted to look at achievements in test scores. So despite gains, they found that African American, Hispanic, and low-income students typically achieve below the levels of Caucasian, Asian, and high-income students. So they also found that African American and Hispanic students also drop out of school at higher rates than do their Caucasian peers. To understand the factors that explain academic successes of these high-risk students, Anderson and Keith conducted a correlational study. They proposed a model composed of 8 variables, which included SES status, ethnicity, gender, ability, quality of schooling, parental involvement, motivation, and academic coursework, and then an outcome variable, academic achievement. They studied one group composed of sophomores in high school who indicated that they were both of non-Asian minority origin and who had a socioeconomic status, or SES, composite scores within the bottom quartile of the SES range. The data collection involved gathering information during the base year, 1980, and then again 2 years later in 1982. But for purposes of analysis, the researchers analyzed data together from both years as if they were collected at one point in time. For all participants, all 7,355 of them, they collected measures on each variable and correlated all variables. They found that each of the variables, except parental involvement, explained a significant amount of variance in academic achievement. So that was our example for explanatory design. Now we're going to look at prediction. The prediction design, you're going to look for, voila, the word prediction in the title. You're going to look at the variables being measured once and then again later, and then forecasting or performance of outcomes within the study. So for example, you can predict a teacher's success in schools with the amount of experience that they have teaching. The outcome being predicted in correlational research is called the criterion variable. Please enjoy this video as a summary and talks a little bit more about correlation and causation. There we go.
If you look at the stats alone, eating ice cream and murders in New York are positively correlated. This means that the more ice cream sold per person, the number of murders increases. Vanilla bean never seems so scary, right? Before you stop eating ice cream sundaes to save innocent lives, think about it. Correlation as a statistic doesn't explain how or why the relationship between ice cream and murder exists. It simply shows that it does. Causation makes an even bolder assumption and says that a change in the number of chocolate cones sold will cause a change in the number of people who meet their unfortunate end. This is clearly a big leap. A well-designed experiment will rule out other factors that could be related. So you must ask yourself, what's another variable at play? It turns out that temperature was also correlated with both ice cream sales and murders because the numbers for both spike during the summer months. When it's warm outside, people simply get out of the house more. They're on summer break or vacation and want a cold, delicious treat. Kids hang out unsupervised more. It just so happens that the Freddy Kruegers of the world also get out more during the summer. Before you jump to a cause and effect relationship when a correlation is found, look at how the data was collected and consider other related factors. And go ahead, eat that pint of Rocky Road.
Awesome. Tissa?
Okay, so oops, going a little bit too far ahead. All right, so now we'll look at the key characteristics of correlational designs. First is the direction. So as Marissa stated briefly before, correlational designs the relationship between variables can be either positive or negative. When the relationship is positive, that means that both variables run in the same direction. So for example, as one variable increases, so does the other increase, or vice versa. The other relationship is that of a negative relationship, and this is where variables move in opposite directions. So for example, as one variable increases, the other variable decreases, or vice versa. Another characteristic of correlational design is the form, which in other words means how does it appear on a graph? It may appear linear. Variables may have a positive or negative relationship, and this relationship can be shown on a graph in a linear format. How do they do that? Well, basically what researchers do, they find a line of best fit. And the line of best fit would be the line that draws closer to as much possible points on the plot as possible. Another form of correlational designs is uncorrelated and nonlinear form. In this, variables are independent of one another. What that basically means is that there's no pattern associated with the variables. They are not related to each other. They are not associated. Another form is curvilinear or nonlinear. Now for this one, I will have to virtually draw what I mean when I explain these things. But overall, curvilinear happens when a variable increases or decreases up to a point where the variables start to change direction. And there are two examples of this. The first one is a U-shaped variable. Now in this example, let's talk about internet use and depression. Now, let's say internet use is your X variable and depression is your Y variable. As internet use increase, depression might decrease up to a point where as internet use continues to increase, depression decreases. Now, I wish I had a chalkboard to show you all of this, but I'll try my best to do it with my hands. So let's start at this point. This is my x-axis, and this is my y-axis. My x-axis is internet use, and my y-axis is depression. Now, on a U-shaped curve, as internet use increases, let's say it's increasing in that way. As internet use increases, depression decreases up to this point where it decides to change direction, and depression increases as internet use continues to increase. So that's a U-shaped curve. Now an inverted curve has the same idea except it's flipped. So let's use the same example. Let's say as internet use increases, so does depression, up to a point where as internet use continues to increase, depression begins to decrease. So basically you just have the opposite, an upside down U. Next, whoops, jumping a little bit too far ahead, degree and strength of association. So Marissa touched upon the Pearson-R correlation, which has values between -1 to 1. The sign associated with the value indicates the direction. when there's a negative sign, it means a negative direction, meaning that variables are oppositely related. And when there's a positive sign beside it, it means that the variables are increasing, both variables are moving in the same direction. Now, the numerical value identifies or indicates the strength of the relationship. The closer you get to 1, the stronger the relationship. Coefficient of determination. So this is taking a little step further from the Pearson-R correlation, and it's basically squaring the Pearson-R coefficient. Now, why would you do that? Well, sometimes we want to know how much of a difference can one variable be explained by the difference in the second variable. So let's say, for instance, we had 2 variables, parent education and student success, which the textbook uses as an example. Let's say we determine that the Pearson-R for that correlation is somewhere around 0.07 or 0.7. Don't quote me on that, but I'm trying. If we were technically to square that R, the textbook explains that the R squared would be 0.49, which would, since coefficients of determinations are reported in percentages, that would be 49%. So this means parent education explains about 49% of students' success. Okay. Next, we'll talk about the display of scores. Display of scores is basically how do we display variables that are correlated with each other? What do we use? We can use scatter plots, which are images to display 2 sets of scores for variables. So scores that are on the x-axis as well as scores that are on the y-axis. At a single point, it indicates the x and y scores for one individual or category. So I'm gonna flip to the other slide for the example of this. So here we're using the same example of internet use and depression. So we have a set of scores for internet use, and we also have a set of scores for depression. And this right here, the graph in blue, that's the scatter plot. At any single point, the little circles, that denotes the scores for internet use as well as the score for depression use. And this graph also shows an example of the line of best fit, which is the line that is drawn on a diagonal in the graph. Another way to display sets of scores is using the correlational matrix. So this is displaying the correlation coefficients, which is the Pearson-R that I mentioned before. So we're not displaying the scores, but we're displaying the correlation coefficients for each variable in a study. And the table there from the textbooks gives an example where we have about 6 variables, there are 6 variables there, and the correlation coefficients associated between each variable is listed on the graph, on the table, rather. Okay, so let's do an activity. Let's guess the correlation from the photo. Okay, can somebody guess what this correlation characteristic is? Sarah.
Would that be a positive correlation?
Yes, you're right. That is a positive linear correlation. Good job. Can someone guess this? Yes, Marissa.
I think this is a negative correlation.
Yes, that's a negative correlation. As you can see, as one variable increases, the other variable decreases. You're definitely right. Can anyone guess this one?
It's positive.
Marissa, do you have anything to say?
Looks pretty random to me.
Okay, right. So first, it is not a positive correlation because as one variable increases, we can't really see that the other variable is increasing as well because the plots, as Marissa says, are random. They're all over the place. This actually shows no correlation. And this is because we can't see any relationship between these two variables. They're all over the place. They're random.
Okay.
Can anyone guess this correlation?
Looks like a roller coaster.
You're definitely right. It's somewhat like that. This is actually an example of the inverted U curve that I've mentioned to you before in curvilinear formed correlational designs. So here, as X increases, Y increases up to a point where as X continues to increase, Y decreases. Sampling techniques. Whoops. Okay, there we go. Sampling techniques. So there's actually no specific sampling techniques for correlational research. Researchers may choose to do different types of sampling in terms of research. However, they may choose to analyze that data using correlational statistical analysis methods. And there are advantages to that. The advantage of using correlational research is that it can be reliable and it can be easily repeated. And also too, it may lead to other research such as experimental research and so on. However, there are some disadvantages to using correlational research, and that is that it cannot establish cause and effect, which the video that was played earlier mentioned. Using the example of ice cream and murders, it appeared to be that there was a correlation with it. However, there was a third variable which was associated between the ice cream and murders, which was temperature. So with that said, correlational research, if not looked into in terms of looking at how the data was collected, could lead to false conclusions, which we all have to be careful for when we are listening or reading media reports. Okay, so a little bit of technical difficulties here, but we're still on track. And we're going to talk about describing and measuring variables. So correlation coefficient, again, this has already been explained. It's the R coefficient, and this is mostly used when the variables are linear. So meaning like they are continuous variables. Another way to measure variables is using the Spearman-Rho correlation. And it's a statistical measure to measure the association between two ranked variables. So these are technically do not have to be continuous variables. The variables should be either ordinal, so in order, intervals, or ratio. And it's used to determine the strength and the direction of those variables. So let me skip to the other slide to make this more clear. Oops. All right, so here we have an example of some ranked variables. So we have physics scores as well as math scores, and they are ranked from highest to lowest, ranking from 1 being the highest and 9 being the lowest. So because we're using ranked variables, ordinal variables, and we want to use Spearman correlation to measure the strength and the direction of these variables. Now on the slide it mentions to measure the strength and direction of the monotonic relationship of the variables. Monotonic relationship basically means, in terms of monotonic relationships can be the same as linear relationships, except that the increase or decreases that happen, it doesn't have to happen at the same rate. So let me skip to the other slide to show you an example. So there we go. All right, so the blue lines underneath the heading monotonic. So as you can see on the scatter plot, the lines appear to be linear. However, as you can see with the arrow is a little bit bent, meaning that the variables are not increasing at the same rate. In those types of situations, a Pearson-R correlation may not be the best fit in order to analyze that data. So we will rather use a Spearman-Rho correlation to do that. And as I mentioned to you before, linear relationships can also be monotonic. It's just that for monotonic, the variables don't always have to increase or decrease at the same rate. Regardless of that, values from a Spearman-Rho correlation, they range from -1 to 1, like a Pearson-R correlation, and it means and it indicates the same when it comes to the sign as well as the strength. Point by serial correlation. So point by serial correlation is another way to measure variables. And this is used to measure the strength and the association that exists between one continuous variable and one dichotomous variable. So example of a dichotomous variable or binary variable is basically a variable that has two categories or levels. Like for example, smoking status. You can either be a smoker or a non-smoker, or you could either be, in terms of economic status, you could either be rich or you could either be poor. So we have one dichotomous variable, for example, smoker or non-smoker, and we have one continuous variable with different sets of values. Maybe like if it's a score thing, it could be a value from 1 to 100, anywhere between that as a continuous variable. So as an example, let's say that a researcher wanted to determine the association between cholesterol concentration, which is measured in millimeters per mole per liters, and smoking status. So your continuous variable then will be cholesterol concentration because it can have any numeric value. And your dichotomous variable will be your smoking status, which can be either smoker or non-smoker. In that situation, we'll use point by serial correlation. Now, the statistical methods of analyzing all of these things are beyond this course, so this is just a brief overview of what they are. Oops. Okay, phi coefficient. So this is another way to describe and measure variables. And the only difference between this one is that it measures the association of two dichotomous variables. So now we have two variables that are binary, which means that they only have two categories. All right, so taking a look at the slide here, variable y has two categories and variable x also has two categories. Now, just to give a very simple explanation of how what a phi coefficient is that you will add up how many individuals or participants or whoever is involved in the study has both variable x and y according to their category, and that is shown by the a plus b or the c plus d, the a plus c or the b plus d. And on the other side of that chart right there, we see the values that can be assigned to a phi coefficient. 0 means that there is no relationship between the variables, and 1, it means that there's a perfect positive relationship, while as -1 means that there's a perfect negative relationship. And I have a few slides just to show you a quick example of that. So positive phi coefficient, in this example, we have the variables gender and marital status. For gender, the two categories are male and female. For marital status, is married and single. Now, and in the numbers here shows how many people are male and married, how many people are male and single, which is 2, how many people are female and married, which is 1, and how many people are female and single, which is 5. Now, researchers will take a look at the appearance of this chart to determine whether or not there is a positive relationship or a negative relationship or no relationship at all. In this example, this is a positive relationship because most of the data are on a diagonal, which is highlighted in yellow. In this example, using the same example with gender and marital status, this would be a negative relationship because most of the data appear on the off-diagonal cells. So as you can see, there's a greater number of people who are male and single, and there's a greater number of people who are female and married. And that is off the diagonal, which means that that would indicate a negative phi coefficient. In this example, using the same gender and marital status, this will show this would indicate no relationship because on the diagonal, the diagonals are the same, whether it's diagonal or off diagonal, the values are the same. In this example, we have 5 and 1 and 5 and 1, which indicates no relationship. However, the values were 1, that would also indicate a 0 relationship, which means that there is no pattern. All right. Multiple variable analysis. So multiple variable analysis. So this is predicting the outcome based on more than one independent variable. So in the previous examples, we were for example, in the internet use and the depression example that I used, there was one independent variable and one dependent variable. But things get a little bit more challenging when it comes to having more than one independent variable. And this is where multiple variable analysis comes in. And there are two ways of doing this. There are two approaches. A partial approach, sorry, excuse me, partial correlations and multiple regressions. So for partial correlation, whoops, skipping ahead. Partial correlation is used to determine the amount of variance that a mediating variable explains in both the independent variables. So what am I talking about? So let's say you have two variables. You have an independent variable and a dependent variable, right? But there's a variable that stands between those that actually affects both. This variable that stands between them has an association with both. Now, in this situation, researchers want to know what happens if we take away that middle variable. How then can we determine the relationship between the independent variable and the dependent variable without the effects of the mediating variable? And this is where partial correlations come in. Oops. So, for example, in this graph right here, we have an independent variable, which is age, and we have the dependent variable, which is comprehension. However, there's a variable that stands between them, which is reading, or the number of the amount of reading one individual does. So that variable stands between. As you can see, reading is associated with age, and reading is also associated with comprehension. But researchers want to know, like, apart from this mediating variable, what is the relationship between the age and the comprehension? So researchers then will calculate, which is highlighted where the A is located. They will calculate what that variance is right there where the A is located using partial correlations. Multiple regressions. So again, this is another approach. And with multiple regressions, it uses what is known as a regression line, which is the line of best fit that I touched upon briefly earlier. And again, that's the line that that comes the closest to all the points on the plot as possible. And that line actually has an equation, which is shown on the slide. Y equals bx plus a. Y would be the predicted value or the outcome, and x would be your independent variables in the study. But however, things get a little bit different when you have more than one independent variable, which is the x. And the equation is the same thing. It's just that you include more than one predictors within the equation, denoted by the equation that is at the bottom right there, y equals b1 x1 plus b2 x2 plus, and go on so forth until you've covered all of the independent variables. Complicated situations. So if things aren't already a little bit complicated enough in terms of adding on all of these independent variables, regression tables are also used in correlational research. And what regression tables do is it shows the overall amount of variance explained in a dependent variable by all of the independent variables. And it shows that with something called the regression weight, so which is the amount of contribution of each variable controlling the variance of the other variables within the study. So basically we have a whole lot of variables, independent variables, dependent variables there, and just a lot of variables. And we just want to know how much are each variables contributing to the variance of the other variables. The beta of coefficient indicates the magnitude of prediction for a variable after removing the effects of the other predictors. So now we want to isolate this variable and indicate how much influence this one variable has on the dependent variable after removing the effects of the other predictors. And that's what a beta coefficient depicts. Again, this is a statistical procedure that is beyond this course, and we wouldn't be able to cover it at this time. But all in all, that beta coefficient will allow the researcher to compare the strength of one predictor variable or one independent variable with the strength of the other variables. So you just want to know what's going on between the whole shazam of independent variables. Oops. Okay, meta-analysis. So we've heard of meta-analysis before. Well, maybe you have. And basically, just as a quick overview, meta-analysis is basically taking a whole lot of studies, different number of studies based on the same or similar subject, and just figuring out, like, trying to understand all of these studies all together. So it's basically you want to derive a conclusion from a large number of studies on the same topic. In correlation, meta-analysis is used to determine the overall correlation coefficient from a set of correlations. So basically, imagine a topic of depression, and we had a bunch of correlational studies on depression that measured variables related to depression, and all of these studies, all of these studies came up with correlation coefficients, and I just showed you an example of that on the screen. All of these studies came up with a bunch of correlation coefficients. They each had different sample sizes, and basically a meta-analysis of these correlations is aimed to determine what the overall correlation would be from all of these set of correlations. And there are statistical methods to determine that. It's called the Hedges-Alkin and the Hunter-Schmidt method. Again, beyond this course, but just for your knowledge, there are statistical methods used in terms of determining what the overall correlation coefficient could be. All right, and take it away, Sarah.
Thank you. One moment. Okay. 1 second. All right, sorry about that. Okay, so hello, cats and kittens. If you recently watched the Tiger King documentary, you'll get that joke. And if you haven't seen it, then please ignore it because it's not funny anymore. Anyways, I'm here to talk about ethical issues. So I know we've spoken a lot about ethical issues within the SSW program, especially a lot in counseling. And within the research program, or course, I mean, what I'm going to talk about is more in relation to correlational design, but I'm sure a lot of it will apply to other areas of research as well. So ethical issues can definitely rise in correlational data analysis, especially when appropriate controls are not measured. So the controls that I'm talking about are things like age, race, and gender. So especially when these controls are pointed out that have been omitted from the analysis. So a good solution is to use a conceptual model or theory to guide the selection of the variables for measurement. So then that way all predictors can be accounted for, everything can be kept track of, which is really good. Also, it's really important that researchers don't edit or make up any data. I feel like that's pretty clear, but I mean, some people need to be reminded because otherwise it wouldn't be within this list. Also, you have to make sure that you report effect sizes and null hypothesis. And while measurement errors do occur, we do want to keep them limited because, for example, when the sample results differently, they differ from the population estimates. That's like a big no-no, so we want to try to avoid that. And when a researcher has outliers within their research, they need to be upfront and honest about it. If they want to remove those outliers, they have to have a good reason for it, and they shouldn't really be sketchy about it. And as well, you want to make sure that you're competent in being able to analyze your findings and provide a properly abstract and analyze those findings of various studies. So you basically just want to make sure you know what you're talking about. Okay, and these ones are pretty straightforward, but I still think they're worth mentioning. So obviously we don't want to hide any contradictory findings or things that don't necessarily align with our hypothesis. While I understand how it can be disappointing if that's not what you were hoping for, you need to be honest about it and make sure that you are sharing your findings. Because if you do hide them, that could definitely change and alter the results and the patterns. Publishing the same results is something that we want to try to avoid doing because it's not very ethical. And like I said earlier, kind of with hiding contradictory findings, don't omit any negative findings. And finally, plagiarizing. Don't plagiarize. Don't do it in your research papers. Don't do it in class. Just avoid it altogether. As you can see with that little meme from Mean Girls, it's against the rules and you cannot sit with us if you do it. Okay, so now I'm going to talk a little bit about the 6 steps in conducting a correlational study. So step 1, first you need to figure out if a correlational study best addresses the issue. So normally, kind of, it was touched on earlier, we use correlational study when we want to study a problem that requires an explanation or identification, or if we want to see that there is an association. So I think a good example maybe would be we want to see if crime rates go up when there is a stronger police presence. So that would be a type of problem we want to use with correlational study. And that way as well, we can examine the multiple factors and variables. Step 2, we want to identify the individuals to study. So it's best to study random participants. So don't pick your best friend and your best friend's family and her family and all the people that you know. You want them typically to be random. And make sure that you have permission from the responsible authorities and that you have that international review board check mark to give you the go-ahead. You also want to make sure that your sample size is large enough, because the larger the sample is, the better you can apply it to the general population. And number 3, you want to identify 2 or more measures or instruments for each person within the study. So by doing this, you can go to other literature and seek what other instruments they used if you're not really sure where to go with it. And then the more instruments you use, it will also help with your accuracy and your credibility. Number 4, collecting the data and monitoring potential threats to the validity of the scores. So you want to administer the instruments and collect at least 2 sets of data, which was mentioned earlier. This allows you to observe the association between the 2 variables for the predicting of a single outcome from a single predictor variable. Number 5, then you're going to analyze the data and represent the results. So using statistical procedures, then we can determine the strength of the relationship and the direction. So as mentioned before, whether there's a weak correlation or not correlation, sorry, there's a weak relationship or a strong relationship or positive or negative, or maybe no correlation at all. Then you can look at the pattern of the responses. Now just remember, just because there is a statistical relationship does not mean that there is a cause and effect. effect. It's just an association. And then you can use the appropriate statistics to use and figure out whether it's linear or curvilinear, as Tessa mentioned, by using a scatter plot. Number 6, you're going to interpret the results. So what does it mean? You need to look at the results and also make sure you're discussing the magnitude and also considering the impact of any mediating variables. Now I'm going to talk about the indicators of a high quality correlational study. So basically to get that big A+ to make sure that you do a good job. So first of all, you want to make sure that you have an adequate sample size. The rule generally is that you have at least 30 participants. However, that's kind of the minimum. The more, the better, as we mentioned earlier. I have a feeling it's probably pretty hard to get participants during the coronavirus right now. So hopefully that kind of shoots up again when everything goes back to normal. Then you want to make sure you complete a correlational matrix or have some sort of graphs present. People love pictures. People learn better. It's nice to see the scatter plots and the line of best fit, or if there is nothing, no correlation, it's just easier to see better. As well, to select the appropriate correlation statistic and report the strength of the relationship. And then it's definitely handy when the predictor and the criterion variable are identified, as well as the p-value and effect size and confidence intervals. And like we said earlier, having that visual model is absolutely helpful for our readers. So if researchers can provide that, then it is very helpful within the studies. Okay, now I'm going to talk about the study that we looked at. This study is called the Self-Efficacy, a Mediator of Smoking Behavior and Depression Among College Students. So this is a correlational study, and we identified it as an explanatory study thanks to all the help we got from Marissa earlier on within the PowerPoint, who explained exactly what that meant. So basically the study was that they wanted to see and test whether there is a relationship between smoking behavior, the dependent variable, and depression and smoking resistant self-efficacy, which is the independent variables among college students. Just to kind of clear it up, the SSE, the smoking resistance, is basically the belief that one can resist smoking behavior, and it's actually been theorized to be positively related to the avoidance of smoking behavior. The sample size for the study was quite a large one. It was 364 college students. So researchers went to a senior college up in New York State, and they administered the survey to about 364 students ages 18 to 21. It was an anonymous survey, so students could choose whether they wanted to do it, and it was a convenient sample as well. And out of the 364, 99 of those students were identified as smokers, and that meaning by reporting smoking within the last 30 days. The instruments used, there was a variety of them, which, as we noted, is a good thing. Instruments used the demographic sheet about their smoking behavior, so whether or not they had smoked a cigarette within the last 30 days. And then the Beck Depression Inventory. You might have heard of this in other studies that you've read, or just generally maybe in a psychology class. It is an inventory, so it's a 21 self-report item that measures affective, somatic, behavioral, motivational, and cognitive symptoms of depression. And then the SSE scale, another self-administered tool that measures the perceived self-efficacy of an individual to resist smoking cigarettes. And then as well, the demographic sheet to determine things like gender, race, possibly socioeconomic status, and things like that. So the hypothesis that they tested, or the following that are shown on the screen, I'm not going to read them all because there are 4 of them, but essentially I think mainly was that they thought there would be a positive relationship between depression and smoking behavior. So the findings. All hypotheses were supported, and they did find there was a statistically significant positive relationship between depression and smoking behavior. So they did hypothesize right, and their evidence had supported it. And luckily, because they used so many instruments and they had a larger sample size, there is a little bit more credibility to this study. But yeah, that is the study. So we just want to thank you for tuning in and listening to our virtual presentation. If you have any questions at any point in time, feel free to shoot a message to any of us. Thank you for listening.
Hope everyone's safe.
Thanks, everyone.
Bye, guys.